Very good. Okay, so let's begin.
Yes.
Good afternoon, everybody. Sabse Jai Bhim. Welcome to an invitation to data science. These are introductory formal lectures that we're going to begin the course with, and the goal here is primarily to introduce some very important important concepts. And although you may have read in the course syllabus that we don't assume anything beyond standard 10 mathematics, this is not for you to think that we're going to give you a kid's version of data science. What we mean by that is that we are going to give you a conceptual introduction, but arranged in a way that we're putting all the mathematical details or the advanced mathematical details to a later version, a more advanced version of the course. And the reason for that is twofold. First of all, is our intended audience is to get people who know nothing about the subject into the subject, but also for those of you who may have the necessary mathematical background, it's better to sort of see things in a simpler context. And even then, it's not necessarily, you'll find it's not that simple. There's a lot of very deep concepts we're going to be covering, but with a minimum of distraction. And so if you haven't seen the introductory lectures that Ramiz and I gave last week, please do take a look at them. I invite you to take a look at them. And the way these lectures will be structured, at least the introductory lectures, is that we're going to pick an application, and via that application, we're going to introduce all the concepts that we need along the way. So the first application we'll be lecturing on has to do with the current pandemic, because it's rich in concepts of statistical inference and data science. The next lecture that Ramiz will give on will be on fraud prevention and fraud detection. And then the third one will be on election polling in general. And as these lectures progress, all important concepts will be highlighted in red to begin with. So the first time you will see them, they will be highlighted in red, and we will spend some time thinking about them. Now, when we first planned these lectures, we thought we could go through an example per lecture. We very quickly realized there's far too many interesting things going on to rush through this. So some applications will actually take more than one lecture, as will be the case with this particular example of COVID-19. So this will occupy us over the next 2 lectures. And I would like to stress that we will be recording versions of these lectures. So so in different languages. So Ramiz will be recording a Hindi version. I'll be recording a Marathi version. So if you find that my English is too hard to understand, I understand that some people find that I speak very fast. Then please take your time and listen to the lectures in the language you're more comfortable in. And I hope, and of course, we're available for questions, any questions you may have on the weekly Q&A sessions that we will organize. So let's begin. So this is on this slide. I'm just listing all of the core concepts that even in this simple example of dealing with how to understand some of the statistics that you've come across in the context of the current pandemic. These are all of the core concepts that we will be coming across even in the first 2 lectures. And this is a lot, okay? Some of these words here, we'll go through them one by one. Some of these words here, correspond to some of the most deepest, most fundamental aspects of the science of uncertainty, and statistics and probability. And we'll go through them one by one as we go through the material, and all of them will be useful in some way as you go on to be as you progress in data science. Now, there are often courses you could look up online or pull up a textbook where they sort of hide some of these concepts from you because they're worried that it's too much. Maybe it's too advanced or maybe it's too confusing. The problem with that is, well, the advantage of that is that you can have a no-nonsense introduction and get very fast, very quickly. But like learning a language, I think most Indians are at least bilingual or trilingual. You speak many languages. We just learned this when we were children, because children are geniuses. They learn very quickly. But we're now all adults, and unfortunately, we're not as smart as we were when we were children. And so we need some structure to our learning. We're not just able to absorb concepts for free like we did when we were 5. And if you try to learn a language now, you will find that if you don't pay attention to some of the grammar, if you don't have a formal introduction to the language, let's say tomorrow you wanted to go and learn Russian or Chinese, of course you can get very, very fast, very far without knowing the grammar. But you will find that your knowledge stops increasing after a certain point, and you will just slow down and plateau. If you have the strong foundation from the beginning, your progress will never be limited. You will just keep going. And the reason we're not going to hide these concepts from you is because we want you to really understand what's happening. And as you will see, perhaps the style of lecture that Ramiz and I give is that we like to be very, very intuitive. And this is not just because we're lecturing students at Digital Nalanda. This is how I lecture my physics students at my university. Because for me, knowledge is not about being able to reproduce formulae in a book or be able to obtain the correct answer to a question in an exam. Knowledge is being able to explain the material to somebody else. Okay, that it means that you must have ownership over the material. That is true knowledge to me. And this is where we're going. So although it might begin at an elementary level, it's going to accelerate very fast, but it will accelerate in a way that you should not feel that there's something missing. All the tools that you need to get from point A to point B will be in front of you. The only missing ingredient will be hard work and really practicing the material and really going over it. So with every lecture, on top of the slides, I will try and set some problem sets to try and help you solidify your understanding. Many things in mathematics, I say, are like kung fu. You don't learn kung fu from reading a book. You learn kung fu by going to a master and learning all the moves and practicing. Okay, so this is where we're going. So bear with me. It starts basic, but it gets very, very advanced very fast. And moreover, there's going to be some notation. Okay, so mathematics is a language, and languages get written in a language, in some script. And there are some very, very, and if you're not used to seeing some notation, it's going to take some practice. So you're going to have to go away. If you've seen it before, fantastic. But if you haven't, it's going to take some time for you to actually get used to viewing these things and seeing how they're presented. Okay, so let's begin. Let's go through all of these concepts. I won't dwell on them here on this introductory slide. This is just for you to see where even by the end of this lecture, we're going to get to here. And the beginning of the next lecture, we're really going to apply all of this. We're going to start applying some of it, but we're going to really apply it to things that you are, most of you have been dealing with and thinking about for the past year. So let's begin. So probability, what is it? Okay, we are all intuitively familiar, we think, with the concept of a probability. But the way in which we understand it actually is actually a very specific sense. And that sense is actually known as the frequentist interpretation of probability. So if we say that the probability of something happening is, let's say, 0.5, or 0.3, or 0.862, intuitively we think that means that on average, the thing happens 50% of the time, or 30% of the time, or 86.2% of the time. Okay, so this idea that probabilities somehow implicitly encode frequency of occurrence is known as the frequentist interpretation of probability. However, by the end of this, these first two introductory lectures, I will invite you to another view of probability, and it's known as the Bayesian view of probability. And it's actually not a frequentist. It's not interpreting things in terms of frequency, but in terms of degrees of confidence. And it's a subtle shift. And it actually sort of just takes something that you've been staring at your whole life and forces you to look at it in a slightly different way. And the power of Bayesian reasoning is that you can do much more in the absence of certainty, in the absence of having complete information. And so it's another tool that is very, very crucial to all of data science, especially when we're dealing with large data sets. So to keep going, the simplest example, and this is a vehicle that we will be using again and again and again, because it's so simple, and because it's so simple, we can really build off a lot of complicated concepts from it, is a coin flip, okay? So a coin flip is a very simple experiment. You flip a coin, and either it lands heads or tails. Okay, so what is heads and tails? It's a terminology from Europeans who put a face on one side of the coin and something else on the other. So we call them heads and tails. We'll be using that language, but in India, of course, coins have a Trimurti on one side and a number, or maybe Gandhiji on the other side. There's many different coins now. So, but nevertheless, we'll still be using the concept of heads and tails. And well, we all know what happens, right? So if we flip a coin, half the time it lands heads, half the time it lands the other side, the tails. But let's say we didn't know that. Okay, imagine I'm some crafty guy in some circus, and I'm playing some gambling game. I'm trying to cheat my customers, and I made the coin unfair. I put a lot more metal on one side, so in fact it likes to favor one side over the other. So let's say we don't know if the coin is fair, and somebody asks you to test whether the coin is fair. So they give you a coin and ask, is this a fair coin? So how do we do that? Well, let's just do an experiment, right? So the obvious thing to do is, we take a coin and we flip it, let's say 10 times. And if we assign, let's say, a value 1 to every heads that we get and a value 0 to every tails that we get, we can basically take the average number that we end up after that 10 trials, and we get 4. Okay, so every heads we give a 4. So the average number of heads after 10 trials in this particular example is 4 out of 10. We want that number to be, we expect that number to be 0.5, but that doesn't always happen, right? I mean, you can take out a coin right now and try, and you see what happens very quickly. Okay, is that you're never always going to get the exact idealized average outcome. And so, but of course, if we did this an infinite number of times, all the way to infinity, then we would get 0.5, almost certainly, if it was a fair coin. If it wasn't a fair coin, then we would very quickly converge to whatever that number is, and we could then test whether that coin was fair. So if that number came out after an infinite number of trials to be 0.6, then you can say to your guy, hey, why are you cheating me? This is not a fair coin. And we would know. But in the absence of that knowledge, how do we try to figure that out? And the core problem in all of data science, in all of statistics, is we never have the luxury of an infinite number of trials. We're only dealing with a finite sample size. And so that problem is our first core concept that we're going to come across today, which is sample variance. Is that the central problem is trying to understand what the underlying randomness is. What is the true nature of the underlying randomness? In this case, what is the true nature of the underlying probability assignment for the coin to land either head or tail? And in trying to understand that with a finite sample, you get fluctuations, okay? And that fluctuation is called sample variance. And this is expected, okay? And in fact, one of the ways in which you can actually often catch fraud So Ramiz will cover this. Or for instance, in a scientific experiment, if you can actually tell when people have made up their data, when they're really just cheating, is when the data looks too perfect, is when it looks too random, because very often that there will be weird fluctuations that you can't explain. This is the nature of life. There are always going to be strange things that you can't explain, because life is a bunch of random chances happening all the time everywhere. Okay, so the important thing to realize is that we need some way of estimating what it is we're trying to understand. Okay, so the thing we're trying to estimate is the probability that the coin will land a heads. So if we were to estimate that by doing an experiment, and every time a coin lands heads, we take the number 1, and every time it lands tails, we assign the number 0, and we sum all of those numbers, and we divide by the number of trials. That is known, in the technical term for that is an estimator. You will see this concept coming up again and again. We have an estimator for what the fairness of the coin is. And what's important to realize is that estimators can themselves actually be biased. So either an estimator is biased or it is unbiased. Okay, so this average that I described actually turned out to be an unbiased estimator, in the sense that if I just assigned 1 for every heads and 0 for every tails, and then I sum those numbers and divide it by the number of trials, after an infinite number of trials, that number will converge. That number will go towards 0.5 if the coin is indeed fair. So that is an unbiased estimate. But not all things that you try to estimate turn out to be that way. And in fact, some quantities are biased. This is something that we will see in a little bit. But actually, I think maybe it's actually quite fun to actually see how this works. So we're going to do an experiment now. Where, of course, it takes a little too long to actually flip a coin every time. This takes forever. So we're just going to give it to a computer. Okay, so if you excuse me for a second, I'm just going to pull up something. I'm going to, hang on a second. I'm just going to pull up actually, I can keep sharing my screen. Yes, okay, so let's see, coin toss. So we're going to do this experiment. And don't worry. So obviously, in the next iteration of this course, we'll actually have code that does this. But all I wanted to show you is here. There's a simulator for a coin toss. Okay, can everybody see my screen? Can you let me know if you can see my screen right now?
Yes, sir.
Yes. Okay. Okay. So don't worry if this doesn't mean anything to you. All I'm doing here is just pay attention to this number here. Okay. This here. Let me make this bigger. This number here is the average result of 1,000 coin flips. Okay, so I've set up a fair coin. Okay, that half the times it'll land heads, and half the times it'll land tails. And I'm just going to do a simulation of what happens if I flip a coin 1,000 times. Okay, look. So one time I get the result 0.501. Another time I get 0.506. Another time I get 0.497. Notice that I never get 0.5. Okay. Moreover, sometimes, like this case, it's actually quite a bit away from 0.5. I mean, if you think 0.528 is close to 0.5, I assure you that if you're running a gambling scam and you can weight a coin to be this unfair, in the long run, you're going to make money. Okay, you're going to cheat your customers. So, as you can see, even with 1,000 flips, you look at this one. You're never really quite at 0.5. You get random scatter. Okay, so now let me do the following thing. Let me repeat this experiment. So I take 1,000 coin flips and I take an average, but then that experiment itself, I repeat 10,000 times. Okay, so this is 10 million coin flips. And I just plot what the outcome is. This number has to get to 10,000. And eventually we will see a graph emerging. Okay, so this is the result of doing a trial of flipping 1,000 coins, doing a coin flip 1,000 times, calculating the average number of heads I've seen, and then repeating that 10,000 times. And this is what I end up with. Okay, so let me go back to my lecture and show you a particular outcome of having done that. Okay, so I did 10,000 trials of the average of 1,000 coin flips, and look at the most common value that I get. It's in fact not 0.5. Okay, so imagine these are not 10,000 trials, but 10,000 individuals. 10,000 people go away and repeat this experiment of flipping a coin 1,000 times. It's going to take each of them a long time because it takes a long time to do that. Then the most number, more than 260 of them, 70 of them will come back and saying the coin is unfair. Of course, some of them, say the coin is, well, I mean, it's unfair in different directions. Some of them even find, there's like 1 or 2 individuals that find that the coin is extremely unfair. But on average, you see, if we look at on average, enough of them, things sort of tend to this funny shape that Ramiz introduced in the introductory lecture. And this is a very important shape in nature. And what we find is that, in fact, not only do we never reproduce, 0.5, that in fact you shouldn't reproduce 0.5. That's impossible. Okay, if everybody came back with 0.5, you know that someone's committing a fraud. Okay, it's cheating because in any given enough trials, you expect to see random fluctuations. There have to be them, and that random fluctuations in the context of trying to understand what the true distribution is for us called sample variance. And so for n trials, in this case, it's 10,000. You expect the result to be scattered around the expected mean, which is 0.5, with a width of 1/2 square root of n. This comes from some mathematics that we'll develop as the course progresses. So what we're seeing here, by the way, if you just can see this guideline shape, is that after an infinite number of trials, the outcomes will tend to this thing called the normal distribution. It's also known as the Gaussian distribution. The two names are interchangeable. They're named after Gauss, the mathematician who first came up with this. He's also the Gauss that if you've ever had to measure a magnetic field in your lab, or maybe you've seen some electronic devices, that's what Gauss corresponds to. And the fluctuations around, you expect to see these fluctuations. That's the nature of the beast. And all of these little wiggles away, this is your sample variance. So this is the problem, okay? We're trying to deduce the mean, but with only a finite number of trials, we're always going to be messed up. Of course, if that n went to infinity, this variance gets less and less and less, and the whole thing becomes more and more sharply peaked. That's how statistics works. That's how sample variance works. And there's a very, very, very deep underlying fact of nature here, which we again will present to you after we learn a bit more mathematics in the more advanced iteration of this course, is that for a sufficiently large number of independent random variables, it doesn't matter how they're distributed, how their probabilities are arranged. For enough of them, all distributions, if they're independent, will tend to a Gaussian. This is why it's such a universal distribution. And that phenomenon is because of this thing called the central limit theorem. It's one of the central concepts of statistics. I'm just introducing the idea here. We will derive it in more advanced classes, but that's essentially what we're seeing is that this is a universal form of uncertainty. So many things in nature correspond to this. I think as Ramiz had this example of this video of dropping balls down a maze, and the maze, balls scattered down this maze, and eventually they piled up in a shape that looked like this. This is more or less what corresponds to the distribution of heights and weights in a given population. So it's a very universal distribution. So look, we've already covered some very, very interesting concepts. We've already covered the concept of sample variance, and we've already covered the concept of an estimator, which was figuring out how to evaluate this thing. So now we're going to take this example and be a little bit more abstract. Okay. So we need to, in order to understand this in a bit more detail, what is it that we're trying to model here? Okay. What we're trying to model is that there's a set of possibilities to which we want to assign a set of probability. Okay, so consider some set of outcomes of some process. Okay, so this is when we're going to begin to introduce some abstract mathematical notation. If you're used to it, fantastic. If you're uncomfortable with it, this is when we're beginning to take the concrete and try and represent it using some abstract terminology and notation. Okay, that's what mathematics does. It allows us to reason much more economically than having to say the words all the time again and again. Okay, so that's why mathematics is the language of a lot of things in nature. So just consider a set of outcomes for any process. Okay, and a set is just a definition for a collection of objects. It could be numbers, it could be, it could be collections of oranges, it could be anything. A set is just, it means a collection of objects. So the set of all outcomes for a coin toss, it's simple. It's just two objects, heads or tails. If it's a dice, the set of all outcomes is all the possible outcomes of a dice. It's 1, 2, 3, 4, 5, 6. Okay. There are also more larger possible sets of outcomes, such as the heights of all standard 10 children. Let's say in Varda Taluka, right? So in meters, it's just a collection of numbers. So the set of all outcomes is just a space of possibility. Now, a random variable is a quantity whose outcomes lie in some outcome space, okay, in the set of all possible outcomes, to which we can assign a likelihood, a probability. Okay, so if the space of all outcomes is heads or tails for a coin, then we make the assignment. The probability of heads is a half. Probability of tails is a half for a fair coin. We could have made it differently. But that assignment to each possible outcome is known as a probability distribution function, or PDF for short. Okay, you'll be seeing this abbreviation quite a lot in what follows. Is just if you take any set of outcomes and you just say, well, this one is going to happen half the time, this one's going to happen 1/3 of the time. That assignment is called a probability distribution function. And so for dice, obviously it's 1/6 of the time for a perfectly fair dice. You're equally likely to find a roll of 1, or 2, or 3, 4, or 5, etc. For a perfectly fair dice after an infinite number of trials. So that's what a probability distribution function is. Notice that random variables and their outcomes can either be discrete or continuous. Okay, so discrete outcomes are things that are like it's either heads, it's either tails, it's either 1, 2, 3, like for dice. A continuous outcome is things like what is the height of an individual? What are the heights of people in a given country? There it's continuous, right? There's no, it's not that suddenly someone is 154 centimeters and suddenly they're 1 centimeter taller. That's not how it works. It's a smooth continuum. So the way in which we're decided to proceed with these introductory lectures is to only deal with discrete variables. And the reason is because all the core concepts can be introduced using discrete variables without having to deal with the mathematics of continuous variables, which requires us to know calculus. So in standard 10, maybe some clever people will have learned calculus, maybe they haven't, but our goal is to do everything without knowing calculus. And in the more advanced lectures, we will teach you calculus and teach you how to do everything for continuous variables as well, which is important for applications such as machine learning, well, at least the more interesting applications. So that's it. So that's what a probability distribution function is. It's just an assignment of probabilities to a given outcome. That's it. Okay. So we have to think a little bit more though. It's not just that we just we assign any given outcome. The probability has to be some number between 0 and 1, because that's basically what probability means. Either it's impossible, so the probability is 0, or it's certain, in which case the probability is 1. Or it could be in between. Usually it's something in between. So in general, given a random variable and given a set of outcomes, the PDF assigns a number to that set of outcomes, but those outcomes could be, they could be anything, right? They could be some small number 2 for the outcomes of a coin toss. It could be 6 for the rolls of a dice. It could even be, in principle, up to infinity. Of course, in practice, never really. But if you imagine the random variable being how many calls do you get in a call center per hour? Well, you can get 1 call, you get 2 calls, you get 55 calls. you get 150 calls. Of course, it's becoming less and less likely over time, but mathematically, it's unbounded. I mean, you could imagine getting, as many calls as you like, right? And so the outcome space doesn't even necessarily have to be finite. It can be infinite. But typically, it's something very, very large, or it depends on the problem. You have to think about what the problem is. And so the most important thing about probabilities is the very intuitive concept is that this probability assignment must be such that all outcomes will certainly happen. Okay, so either the coin lands heads or the coin lands tails, and so the sum of both probabilities must equal 1. Either the dice lands 1, either the dice lands 2, 3, 4, 5, 6. So the probabilities of all of those outcomes must sum to 1. They can be nothing else. Okay, so over all possible outcomes, the probabilities must sum to 1. That's the definition. And so we've introduced this notation here. You'll be seeing this notation quite a lot in what goes forward. And it's using this weird Greek symbol, sigma. Okay, so sigma means sum. Okay, so if you see something that says sigma goes from I equals 1 to n of some f of x, what that means is you put a 1 in each of the arguments. You put the number I goes from 1 all the way up to n in each of these arguments. This is just shorthand for this. Okay, so if you've never seen this notation before, this is what it means. You're going to have to get used to it. You'll be seeing it everywhere. If you've seen it before, fantastic. It shouldn't be too complicated. But this is all this means. So this is just shorthand for summing this quantity from I goes to 1 to n, and that all probabilities must certainly happen will means that this quantity has to sum to 1. So we also introduce this notation which uses angled brackets, which we simply mean to denote the expectation value, or if you like, the average. Okay, so the average value of it. So what I mean by that is if I wanted to construct, so implicitly we did this when we were using this estimator for the fairness of a coin. We assigned to every heads the value 1. We assigned to tails the value 2. And every time we flip the coin, the probability of getting that outcome is the probability of that outcome times that value. So for heads, it's 1. For tails, it's 0. So if we wanted to calculate the average value when you throw a dice, it means 1 times the probability of throwing 1, 2 times the probability of throwing a 2, 3 times, et cetera, et cetera. Okay. Each dice throw occurs with the same probability. But if we're interested in the average value of the dice throw, we just multiply that outcome times the probability of outcome and just sum. It's a weighted average. Okay, and for that we use the notation of this angled brackets. So for the average value of a dice throw, it's 3.5. Okay, so if you just roll the dice an infinite number of times, or a very large number of times, say n, 1,000,000, you summed up all the outcomes of that dice throw and then divided by 1,000,000, that number would be very close to 3.5. Okay, so this is what this angle bracket notation means. So we're going to progress. It's going to start getting a bit quicker and quicker. So please, I invite you to, see these lectures again in your own time. These slides will be available online, so you can go backwards and forwards as quickly as you like. And we will provide exercises to help you master some of this notation and this material to your comfort. So realize that we can sometimes be interested in more complicated quantities other than just the average. For instance, we might be interested in the average of the square of the outcome of a dice roll, or the cube, or any number, right? You'll see why we're interested in this in a second, but these are things that we could be interested in, right? So so for instance, I might be interested in let's say I'm playing some complicated game where it's not the roll of the dice that matters, but the square of the roll of the dice that matters. Let's say I've cooked up some weird rules for some game, and the value of this game, the number of interest is the square on the dice roll. So what is the average value of the square of the roll of a dice? Well, it's the square of the value of the dice roll times the probability. And so from that, we can quickly arrive at the average values of whatever we're interested in, that is some function of the value of the dice. Okay, and so all of these quantities, they are known as the moments of the distribution. Okay, so the first moment is just simply the average, and the second moment, this is just a mathematical terminology. They're just known as the moments of the distribution. And intuitively, it's just taking the weighted average of whatever random variable you're interested in times that quantity of interest summed over all possibilities. If that's unclear, please ask. I can ask me later or ask me now, and I can try and explain it better. But I hope so far it should be some stuff that you've basically seen before, but perhaps in a different language and notation. So good. Now, the most interesting thing that comes up in statistics is not, the value of a particular quantity, but how much that quantity fluctuates from the average. Okay. Now, why is this interesting? So very often, you're not actually going out there and you're measuring. You're not actually going out there and you're, measuring averages and things like this. You're going out there and asking questions like, how likely is it that I have observed this event, given the underlying probability that I think is happening here? This process is called hypothesis testing. Okay, so imagine you're walking down the street and suddenly you see somebody walk past you that is 2 meters 30, 2 meters 30 tall. It's like, wow, that person is huge. How, what are the chances of me seeing that person? Okay, and then you keep walking down the street and then you see, oh my God, I see another person that's 2 meters 20 meters tall. What are the chances of me seeing two people that are that tall? And then very quickly you realize that the probability is so low that one of the assumptions that you made in calculating your probabilities is probably wrong. Namely, it was a random process. Probably what happened is that there's a convention of tall people happening down the street, and that's why you're seeing so many tall people. Okay, but that process, this is known as hypothesis testing, right? So if you just assume that the process is random, you test what is the probability of me seeing a very tall person, but oh my God, two tall people in the same 5 minutes, and if you find that it's very, very low, then you start to get a sense that maybe something is wrong, and one of my assumptions is wrong, and that assumption is, was this a truly random sample? So the deviation from the average is a central quantity in statistical inference and in probability theory. So let's say we wanted to actually measure this quantity. Well, we're never really, just looking at, we're never satisfied by just looking at one sample. We're trying to take an average of, some n samples. So let's say I go out and I look at the heights of 10, 15 people, and I compare them to the average height in India, say. So that quantity is the random variable minus the average. So, I am 190 centimeters tall. So I think, I don't know, maybe some number of centimeters taller than the average person, where I live, or most places really. But if I averaged over this for not just me, but for lots of people, I get 0. Okay, and that's fairly straightforward to see. So let's actually work through this example for the dice, right? So if I try to take the deviations from the dice roll, so that we just calculated that the average of the dice roll is 3.5. So this average value here is 3.5. And I want to know, what is the average value of the deviation from the average? So what I do is I construct this quantity, and I just take its weighted average. And then just from some manipulations, I can write this sum as two different sums. And because this is a constant quantity, it comes outside the sum. And because this is the definition of the average, and because this sums to 1 by definition, this whole guy is 0. So that wasn't a particularly useful thing to look at. So we have to think a bit harder about how we're going to actually quantify or think about deviations from average. So let's try the square instead. Okay. So since the variable, any random variable minus the average value of that variable, this quantity is going to vanish. Let's see what happens if we do the same thing to its square. I will set an exercise where hopefully you'll be able to prove, it should be straightforward, that the average value of the difference, the square of the differences, can be written as the average of the square minus the square of the average. Okay, and all this is trying to quantify is your deviation from the average. But if you're just looking at deviation from the average, of course, on average, you got equal number of fluctuations above versus below, so that cancels. So maybe you want to square it. So when you square it, that quantity is known as the variance. This is a very important concept in statistics. It's telling you how noisy, or if you like, how intrinsically fluctuating your sample is. Okay, the square of the variance, the square root of the variance, is known as the standard deviation. So for those of you who've done electrical engineering or dealt with anything in electrical circuits, why don't we talk about the mean voltage for an AC supply? Well, it's because the average is zero, right? It's an alternating current and it averages to zero. So instead, we talk about the root mean squared voltage, okay? Because if you take the voltage and its difference from its average to zero and you square it, that quantity is not vanished. It's telling you how the thing fluctuates over time. So we've introduced a concept of probability distribution function, which assigns to a given probability. So this is just a quick recap of what we've seen so far before we move on. And what we've seen is the way we think about random variables in the abstract, not in the concrete. Okay, so it's nice to think about coins flipping and dice, but really nature is much more complex and diverse, and there are many ways in which randomness manifests in the universe. So we want to think systematically. So the way we do it is we refer to any assignment of probabilities for any set of outcomes as a probability distribution function, a PDF. We're going to use that terminology again and again and again. And the core concept is that everything that can happen happens. Therefore, the sum of all probabilities has to equal 1. Okay, that's the definition of what a probability distribution function does. And then we introduced the notion of a weighted average, which is that if there's some quantity that's some function of the random variable, then the expected outcome for that function of that random variable is just the weighted average. It's the function of that random variable times the probability that random variable happens. And so for that, we use this shorthand notation, which is known as angle brackets. Okay, so you're going to see this again and again. I'll set some exercises where you try and get used to this reasoning. This is really how mathematicians write things down. This is really how statisticians write things down. So you're really seeing how people really how everybody deals with this stuff. And we have a special name for the expectation value, the weighted average of the random variable to some power n. We call that the nth moment of the probability distribution function. And of these moments, there are 2 that are particularly of interest to us, which are the average, which is just the first moment, and some combination of the second moments that is called the variance. Okay, and the standard deviation is the square root of variance, and it's just trying to capture how things deviate from the mean. Okay, and we can't have looked at not the square because on average you get equally as many fluctuations above as below, so you have to look at the square. And so in the example we looked at with the coin tosses, the Gaussian distribution is telling us that after an infinite number of trials, the average will be 0.5, but there will be a standard deviation that we could have done for all of our trials, which in this case is 0.158. And this exactly corresponds to this width at half maximum. Okay, so that's what the standard deviation is actually quantifying. It's quantifying the fatness of your distribution. So distributions that have a large standard deviation have much more fluctuations from the mean, and distributions with a small standard deviation are very sharply peaked around the mean. You're only typically finding average values. And in fact, in a country like India, very often I have very frustrating experiences talking to Westerners about our country, because they have an intuition based like this. Primarily for them, they come from relatively homogeneous countries that are relatively small, and where you can talk about concepts like mean and average, and these things are sort of meaningful. But India is a very complicated country, and there are many different many different countries one on top of another. And so people will often say, like, this doesn't really, how do I make sense? Because the normal statistics people have in their mind, so for instance, in in India, I think most Indians look relatively familiar to each other. But I remember, a Chinese colleague of mine in school, and he saw somebody who was, very dark-skinned Indian person. He's Tamil. He's like, how can that person be Indian? He looks nothing like you. And I was like, you see, your reasoning is like this, okay? Whereas for Indians, our distribution is much more complicated. We are what we call a multimodal society. Our distribution is actually, it's nothing that looks quite like this, right? And the reason is that because things aren't necessarily independent. This is a bit of an aside, but the way people form intuitions and instinct is often very much based on this type of reasoning. In fact, believe it or not, a lot of our senses, the way we actually vision, what you might think of as seeing an object, you're never actually just looking at something and have light going from something into your eye and seeing it all the time. That is not how our eyes work. What our brain is doing is it's doing an inference, right? It's doing a statistical inference based on experience. And this is why we often have things like optical illusions, and why very often, we can see things that aren't there, is because our brain is doing a statistical inversion of what it likely thinks is out there based on some input. And the priors, these are all concepts that we will hopefully get into. Maybe it's even maybe optical recognition will be an application we will use. Relies on this type of inference where you put in some sort of prior distribution. But let me just take some questions. But first, let me just finish this section here, and then we can take some questions. But so these are all the the core concepts. So actually, maybe this is a good point to pause. So I want to summarize that up till now, we have covered some very, very deep concepts. Okay, we've seen the concept of frequentist observation, which means that we've assigned a frequency implicitly, but that's not all what we mean by probability. And I think by the end of this lecture, we'll introduce Bayes' theorem. And if you're scared of the words Bayes' theorem, don't be, because when I prove it to you, you will think that is not even a theorem. That is just obvious. Okay, it is a tautology, what they call a tautology, something that is self-evidently true. But the power of Bayes' theorem is in how we take things that we've seen before and we start to reinterpret them. And that is really, really different. And that is going to be the majority of how we shift in our thinking on probabilities being frequencies to being degrees of confidence in a hypothesis. So we've covered a lot already. We've covered sample variance. We've covered a probability distribution function. We've covered moments of the distribution. We've covered the concept of variance. We've covered estimators. We've covered whether the estimators are biased or unbiased. You've yet to see an example of an unbiased estimator. Maybe that'll come up soon. Really the core problem in statistics, in data science, is not only are we ignorant of the true nature of reality, we're even ignorant of how to parameterize our ignorance. Okay? So the way we normally parameterize our ignorance is we assign a probability distribution function to something. But what if we don't know that probability distribution function? We're trying to find it out. We're trying to estimate it. And we can estimate it by estimating the different moments of the probability distribution function. And if we know enough of the moments, we know enough about the probability distribution function, that we can start to make statements. And this process is known as statistical inference. And unfortunately, it's never perfect. And one of the most striking things about nature is it often fools us into thinking that we understand what's happening. And in fact, something else completely is happening. And the biggest example is when we try to model things with a particular statistical model, but it turned out that the statistical model is wrong. This happens all the time. Economic forecasting is this. People that try to forecast the stock market do this. Insurance companies, when they try to insure, let's say, somebody wants to go out tomorrow and get life insurance. Somebody sits down and figures out your odds of dying. That's a calculation they do, right? They look at your medical records. They look at, they look at how old you are, and they have some table, and somebody's done a computation that the odds of this person dying in the next 20 years is X. So if we give let's say 100 of these people in insurance with a premium, and that in every, we expect one of them to die every, let's say 20 years, then we make a profit. That's how they actually calculate these things. But sometimes we can be fooled into thinking we're understanding the moments, the underlying the distribution by sampling the way that we're sampling, and then something really, really out there happens. Something catastrophic could happen. There's a war. There's people think COVID-19 was one of the things. In fact, it wasn't. This is actually people were very aware that the pandemic was going to happen. So this is always an imperfect process, and this is why I want you to be able to think about this for yourselves, because the goal is for you to be masters of your own destiny in life and in science and in whatever it is that you do. And very often the difference between a good data scientist and a not good data scientist is this awareness, this self-awareness that everything is up to degrees of confidence that can always shift under your feet. So you have to be aware of the limits of your understanding. And this is something that we'll be seeing a lot. Now, I don't want you to go away and feel depressed that, oh, we can do nothing with statistical inference. Of course you can do a lot. It's just that you have to be aware that it's never always going to work, because this is just the nature of reality. And in fact, very often it's happened that people think, oh, things are going like this, things are going like this, things are going like this. Maybe this is the underlying distribution for these events, and then something very rare happens, and the whole model is wrong. This happens all the time. So we're going to understand all of this for ourselves, and you will hopefully be able to think through this for yourself. So before I go ahead, maybe this is a good time to take questions or comments, because now we're going to get into some real more details about estimators and whether they're biased and so on, and statistical inference in general. So if there are any questions, please just ask. Diraj, I've noticed that there were some maybe questions in the chat.
Yes, sir.
Yes.
There are two questions in chat box.
Yeah. So please, can you just unmute and ask, or maybe someone can read them out to me?
I can interrupt this. First question is, I have a question. How can data science be used in academic research? From Modish Kumar.
Yeah. Well, anytime you do any science and you do experiments, you need data science, right? I mean, especially if you're dealing with large data sets. So in academic research, for instance, let's say you're in a lab and you're looking at the outcomes of some large number of experiments. The tools and techniques that you need to estimate, to understand what you're doing, draw heavily from data science, especially for large situations we have large data sets, like in genetics or in astronomy. So that's in the sciences. But in the social sciences, for instance, let's say you're trying to understand some economic phenomenon, or the shifts in attitudes via some surveys or something like this. There again, you're dealing with a large number of data points, and you're trying to make sense of them. So essentially, any context in which you're dealing with a large data set is where data science is applicable. So there's many branches of academia where that happens. There's many branches of industry where that happens. It's everywhere.
Next question from Nilesh sir. In such diverse condition, how can we inform the data?
So it just means that you have to be smarter about your priors and how you parameterize things. So let's say, for instance, you have this model where heights are distributed Gaussian in a Gaussian manner, but many things in nature in society is often actually what we call a bimodal distribution. It's actually the superposition. It's the combination of two independent Gaussians. This happens all the time, right? So for instance, if I took a bunch of people from Himachal Pradesh and I mixed them up with people from Bengal and I asked for the heights, because people from the Northwest tend to be a bit taller, then you'll see that the distribution has two peaks. And so if you try to force, if you try to infer using an assumption that you're just looking for the mean and the standard deviation, you'd quickly, start to realize that things are a bit funny. But if you realize that in fact that there's what we call a bimodal distribution, there's two peaks, then you can actually make some progress. And so it's not that you can't do anything in situations where the uncertainty or the situations are different. It just means you have to think a bit harder. And so part of what we hope to do is to engage you in that thought process, is to make you be able to think about why, so the goal of these lectures is to give you a toolbox. And more than just giving you a toolbox, is giving you the knowledge of what tool to use when. Very typically what happens, and this is true everywhere, is that you teach something like this and the students just thinks, I will use this tool always for every problem the same way. And that is not very smart. And that is often going to lead you wrong. And so there's often ways. So the statement is, you have to think about it on a case-by-case basis. But given the self-awareness of what all of these concepts mean and how and when they're useful, you will be able to make meaningful statements and make some use this information in a clever manner and arrive at meaningful information from. That's so this short answer to your question is you can make progress, you can arrive at conclusions, but you have to think harder. Is there other questions?
No, sir.
Okay, so let's continue. So what I will do, what we're heading on to now, is this very important concept of estimating. Okay, so but now seen in an abstract way, not in a concrete example, but they thought of more generally. So let's say we have some random process. Nobody told you what it is, just some random process. And you have n samples, you have n trials. So it could be the outcome of some test, some medical test. It could be looking at some looking at the number of cars on a given section of the road at a given time. You're just repeating the same thing n times. Then it seems quite reasonable that one way to estimate the average, right? That's what this E means, is to just, okay, so notice I'm not using any probability distribution functions here. I'm not using a PDF. I'm trying to estimate what the parameters of the PDF are. What are the parameters of the underlying probability distribution function? So one way to estimate the average is to just take the outcomes and divide by the number of trials. Obvious. I think we all know this. And as n goes to infinity, if we do this an infinite number of times, doesn't matter what the underlying probability distribution function is, you can prove that this quantity will converge to the actual average of the actual underlying probability distribution function. Such an estimator is tending to the true value of the thing it's trying to estimate. So we refer to that as unbiased. Okay. Now here's an unusual example. Well, no, it's an example we just saw, but it's a little counterintuitive actually. But now let's say we're trying to estimate what the mean square is. We're trying to estimate what the fluctuations are squared from the mean of a given number of trials. So we're trying to estimate the standard deviation. So we just do the obvious thing again, right? We just take the outcome of the experiment, we subtract the outcome of the last estimator, okay? Because we don't know what the true mean is. We're just looking at the estimation for what the mean is. So you subtract from what we observed from that estimation of what the average should be, and we square it, and we sum it, and we divide by n. This seems like what we should expect to be what we really mean by the variance, because this looks like what the variance should be for if we actually had the underlying probability distribution function. But it actually turns out that as n goes to infinity, this does not tend to the true variance. In fact, it's off by a factor that goes to 0 as n goes to infinity. But if n doesn't go to infinity, it is said to be biased. It is a biased estimate. Now, we can unbias that estimator by, instead of dividing by n, dividing by n minus 1. Okay? So the difference between the two is very, very little for large enough n, but for a small number of n's, that difference could be quite a lot. Okay? But the point is that for a truly unbiased estimator, no matter what the sample size is, this is the quantity you should construct. Okay, and the reason is actually it's not so complicated, but we will derive it in our next lecture. So I will, since this is about COVID-19, let me tell you of a biased estimator that is really surprising to a lot of people. Let's say you're trying to determine what the case fatality rate of COVID-19 is. Meaning, if somebody has been tested positive, what are the odds that they're going to die? Okay, so obviously, the obvious number you think would be, well, why don't we take the number of positive tests, divide by the number of deaths, right? That seems like a fairly good way to estimate what that outcome is. What we will show, and what I will, the second lecture, what I will point out is this is a bit complicated because actually what happens is that the pandemic is ongoing. It's not finished yet. It's still ongoing. So some people are in hospital, they've tested positive for COVID, but their case isn't resolved. It's still, it's not clear what's going to happen. And so the number that we would have taken, which is the number of positive tests divided by the number of deaths up until that point, turns out to be a biased estimator. It is getting the actual, it's actually quite far away from the true underlying case fatality rate. And the actual biased, the actual unbiased estimator is something quite counterintuitive. And it actually, it involves a different combination of things. It's actually, what is it? It's a number of true cases divided by the number of recovered individuals plus, it's something complicated. You wouldn't have guessed it, but this object actually converges to the case fatality rate much better in the middle of the pandemic. Of course, at the end of the pandemic, the estimator that I had before, which is the number of people that tested positive divided by the number of deaths, that indeed is quite accurate. So that estimator becomes unbiased towards the end, but in the middle of the pandemic, it's quite biased. Okay, so the statement is, let's pause and think about this. Okay, so the statement is, we don't know quantities in nature. We're trying to figure them out. Okay, so if I'm trying to figure out what the average height of people in India are, and I go and I measure people's heights, I can only do that for a finite number of people. So I have an estimate. Okay, my estimate is just the heights, sum of the heights divided by the number of people. I know it's a mathematical fact, it can be proved, that this is an unbiased estimate. That that this will actually go to the true average as n goes to infinity. But if I try to do the same thing for the deviation, for standard deviation, so I'm trying to see how diverse the heights are in India, then it turns out that this estimator is not. I'm going to be off by a finite factor, by a constant amount, which is called the bias. That's why it's called the bias, and that this is a true unbiased estimator. That even for finite sample size, I will converge to something more like the actual standard deviation, the variance, the fluctuation from the mean of the average heights. So these are very central concepts to statistics, because we're never dealing with probability distribution functions. We don't know what they are. We are trying to figure out what they are. And the way we figure that out is using these guys called estimators. Okay. And another important concept in statistics is this thing called the likelihood function. Okay. So the likelihood function is the following object. Now, suppose somebody handed you a coin. We're going back to this coin example again because it's really, everything can be understood just thinking about coins. So, by the way, and I invite you to do this. If there's any concepts that I've covered here that might seem that I've gone a little too fast, just break everything back down in terms of thinking in terms of coins and dice. Okay, because it's all there. Okay, so suppose somebody handed you a coin, but they didn't tell you if it was fair or not. Okay? This could be some sneaky guy at some circus or on the street in Bombay trying to play some dice game with and they don't tell you. And so so how do you figure it out? Okay, so let's try and estimate what the actual fairness of the coin is. So let me leave it to be some arbitrary probability. I don't know. So let's say the probability of landing heads is some unknown value. Say, let's call it theta. Theta is a Greek symbol. I hope you will have. I'm familiar with Greek symbols. Of course, they're used all the time in mathematics, so I presume that's true. So if the probability of getting a heads is theta, then obviously the probability of getting a tails is 1 minus theta, because either it lands heads or it lands tails. So the sum of the two must be 1. Okay. So we can rewrite this as the probability of obtaining a heads given theta is theta, and the probability of obtaining tails given a value of theta is 1 minus theta. So where theta is a half for a fair coin. But we don't know if the coin is fair right now. We're trying to test it. We're being agnostic. We don't know. So we're allowing theta to be whatever it is. Okay. So this introduces the concept of the likelihood function. This is a very, very important function. It's a very central concept in all of statistical inference. And all I'm doing is I'm taking what we already had before us, but flipping it around, flipping the way we're thinking about it, okay? The likelihood function views the outcome of the trial as fixed, but allows the parameters to vary, okay? So if I obtained, I flipped a heads, okay, that probability is, probability of obtaining that outcome is a theta, but I'm now viewing it as that we've obtained heads is a fixed. That is a fixed quantity, and I'm asking what is the likelihood, what is the probability I would have obtained that heads. So I'm calling that theta. So it's only viewed as a function of theta and not the outcome. Okay, so it's just taking the outcome given some parameter for the underlying probability and viewing it only as a function of that probability. So let's make this concrete. Imagine I did 8 coin flips. Okay, and I found that I got 6 heads and 2 tails. That's just what happened. So I invite you to try this yourself. Just take, so what is the likelihood, given an uncertain fairness of the coin, of this outcome? Okay, so so heads, tails, heads, tails, heads, heads. Well, I know that all of these draws are independent. It doesn't matter what order they occurred in. So the probability of getting 6 heads and 2 tails is the probability of getting 6 heads times the probability of getting 6 tails. So I just multiply the probabilities together. Okay, so if the coin is fair, then theta is equal to a half, and so you just get some number. But suppose nobody told you that it's fair, and we're trying to estimate it. Well, we can imagine estimating theta by finding the value that maximizes the likelihood function. Okay, so if I took theta to the 6th times 1 minus theta, theta can be between 0 and 1. And this is parameterizing the fairness of the coin. Both 1 and 0 are completely fixed coins. That means it lands either heads or tails every time, right? That'd be crazy. Of course, in reality, you have to be extremely weighted on one side for that to be true, but it can happen. And somewhere in between is a weighted coin. So if the probability of obtaining a heads was a theta, then the likelihood of obtaining 6 heads and 2 tails is given by 6 times the probability of obtaining 6 different heads and the probability of obtaining two tails, but it doesn't matter the order, so it's just given by this function. If I plot this function as a function of theta, I see that in fact the likelihood is maximized when theta is 0.75. Okay, this is called maximum likelihood estimation. With a finite sample size, what is the likeliest value for the underlying probability distribution function to have given you what you see? Okay, so we live in a universe where we just see something. This is what we see. This is saying that it is likelier that the coin is quite unfair than if it was fair. Okay, but we haven't quantified this yet. We haven't quantified the degree to which we are allowed to ascribe a confidence to that maximum likelihood estimate. But I just want to pause here and point out that this is actually what statistical inference is. Okay, this is it. This maximum likelihood estimation is a central concept in statistical inference, which is you are given some data, you look at the data, and you have some underlying model that could have given rise to the data, but that model depends on some knobs on a box. Okay, in this case, it's just one knob. It's just theta. But in general, it could be many more, right? And these knobs correspond to the averages of certain underlying quantities or their standard deviations. And you're trying to find the setting the settings on that box that best fit what you actually saw. So there's some quantity you're trying to maximize, and that quantity is the likelihood. So the value in this example that maximizes the likelihood is 0.75. So if this is all we have, if all we have is just this, 8 coin flip experiment, the most we can say is that we're liable to conclude is that the coin is unfair. But here again, we come up against one of the irreducible perils of doing statistics with a finite sample. You see, I'm not one of these professors or people that's going to sit here and lie to you and say, oh, everything is fantastic. You can do everything with this. You have to be smart. You have to know what you're thinking about. You have to know how you've been thinking about it. And you have to be very, very aware of the limits of your reasoning. And in life, this is the problem with most people out there, even very smart people, even scientists, is that they're blind to where their framework ends. And this is actually very often why an experience that must come very close to your heart, it is probably impossible to talk to some of your upper caste friends about the injustices of the caste system, because in their minds, they are unaware of the boxes in which they're reasoning, and in their world, everything is, according to how they see it. Okay, we need to be more aware of our assumptions in order to really deduce what's happening out in the universe. And this is one of the perils that we're going to come across when we do statistics. Is that although our maximum likelihood estimation in this case said that it's likely to be, the likeliest value is 0.75, we should immediately realize, but come on, you only did 8 coin flips. Let's do more, see what happens, right? And of course, what you will find is that the more and more coin flips you do, and this is an exercise I would like you to do for yourselves. I'll put it in the exercise book. You should do it. Is just to try it. Do 5 coin flips, with a perfectly fair coin, even, right? And just see what happens. And with a large enough sample, your maximum likelihood estimate will converge to the true value, which, if it's a coin that you got from the street, it's probably a fair coin. Now, I wanted to point you guys to a resource that I use quite often. So if you notice at the beginning, I did this simulation with coin flips. I use this software called Mathematica. It's actually it costs a lot of money unless you're enrolled in an institution that subscribes to it. So I'm lucky enough to do that. And that's what I use to generate all these notebooks and all of these graphs. But I wanted to point you to an online resource that is completely free, that if I just click on this, let's see. Okay. The language is very, very simple to use, but I can, if I want to do things like, it's basically an online scientific calculator. So for instance, if I wanted to plot the function x squared, from x goes from -3 to 3, and then I hit equals, it will generate that graph for me. And so if you don't have access to something like this, or the syntax is very simple to understand. Maybe I'll try and post links to a tutorial for this. But for instance, if we were interested in doing a maximum likelihood interpretation of, let's say, this example that we just used, right? So let's say instead of, let me just write theta as t, and I'm interested in calculating the probability as a function of t of having had 8 coin flips. That plot that I just threw up, you can just generate online, using the software, and you can mess around. So there's some syntax here. This is just to advertise that this is a very useful resource that I encourage you to play around with. Of course, in the next module, we will be teaching you how to code, and so we will have much more powerful, more sort of from the ground floor up ways of doing all of this. But for now, this is good enough. Okay, so good. So this was maximum likelihood estimation, and it is the core. It is the core of statistical inference, the central problem in data science, and by the way, you might see, this might seem like, oh, okay, he's just talking about, statistics, but this class of problem is in everything, okay? If you go to get a medical scan, for instance, and someone fires some radiation into you and presents a scan, and you see some image on a thing, they have used the same mathematics, okay? They're trying to invert what is the likelihood of that there is actually some tissue here versus not. If that's what gives you all of these relief contours, and or for instance, when you're training a machine to try and recognize handwriting, or ask pictures, this is the process that it goes through, but in much more on steroids, right? So it's much more much more advanced. So maximum likelihood estimation is at the core of statistical inference. In fact, it's at the core of a lot of things, and it's just trying to model the outcomes of some random process using some underlying thing that you have some knowledge, some parameters. So here's just a small sample of things that you could be interested in looking at, such as the average heights and standard deviations in a sample of people, or how many infected individuals there are in a locality from the results of random testing. Okay, so right now, coronavirus is coming back in India, so it's a very important question. One of the things that we're particularly interested in science is we're trying to understand some deeper underlying theory. So in my day job, my research is in cosmology. Okay, so I'm trying to understand the origins of the universe and how it came to being how we think we did. And so what we're really doing, believe it or not, is the same thing, where the data points are now galaxies and things that we see, and we're trying to infer what the underlying knobs on the box, and that box is a physical theory, corresponds to. And what we've learned is that 75% of the stuff in the universe is in this strange form of energy called dark energy, that we have no idea what it is. And 25% or 23% is in this thing called dark matter. We also have no idea what it is, but we see its gravitational effects. How do we know this? We did exactly the same process. We looked at data from the sky, and we did a maximum likelihood estimation of the cosmological parameters. And those parameters are today known as our Big Bang cosmology. Okay, so this stuff is everywhere, and its applications are boundless, right? So I really hope to emphasize that just because Ramiz and I focus on certain examples in these lectures, this is not anywhere near the limits of it. These are just examples picked because they show us all the different things in a very simple context. Okay, so there's more than just parameter inference. There's more than just trying to understand underlying things of a statistical distribution. And one of the things that we're also very interested in doing is this thing called hypothesis testing. Okay, and here we're going to need a bit of a shift in how we think about probabilities. Although we're not actually going to be doing very different mathematics, the shift in our perspective is going to be huge. Okay, so let's say, for instance, you're interested in a question: does a particular chemical cause cancer? Okay, now just because you notice that in areas where there's more of this chemical, people have more incidence of cancer. Just because that's true doesn't mean that that chemical causes cancer. It could just be a correlation. So in fact, in statistics, we will go through the concept of correlation and correlated variables and things like this in the coming lectures. But in statistics, the statement is, correlation isn't causation. So you can do this very, very amusing thing, and you can plot on a graph all of the countries where they have the number of doctors per 100,000 people. And you can also plot on that same graph the number of people that have died of COVID per 100,000. And it turns out that the graph looks like this, right? So countries where there are fewer doctors per 100,000 are also countries that there are fewer deaths per 100,000 of COVID. And countries where that they are the highest per capita number of doctors, some of the highest. They also have some of the highest per capita death rates for COVID. So some of the highest per capita death rates are in very advanced countries, like in Czech Republic and Belgium and Sweden and the UK. They also have the highest number of doctors per capita. So does that mean that doctors are killing people? Obviously not, right? So, but that's a very simple example of how correlation doesn't mean causation. So just because you look at some data and you see, ooh, there's lots of chemicals, there's lots of cancer where there's lots of chemicals, it doesn't necessarily mean that that chemical is causing cancer. You have to think harder. You have to do a few more statistical tests to really see if that's true. And so a very important tool in this process is called hypothesis testing, and in particular is a Bayesian hypothesis testing. And in order to do this, we're going to have to introduce a few more basic concepts. So at the list we saw at the beginning of the lecture, we're really going through a lot of these things now very fast. And the concept that we're about to introduce now is conditional probability. So very often, we're interested in situations that involve more than one random variable. So let's say you have two multiple dice. You're playing a game where there's two dice. Or there's a game where you're flipping one dice and one coin. Okay? And so let's say you're interested in the probability of two things happening. So the probability of X and Y is the mean, which means the probability that both X and Y occur. Okay? So for example, one dice rolls a 6, the other dice rolls a 2. What is the probability, or for instance, or the probability that you have a game where it's one dice and a flip of a coin, so you roll a 6 and you flip ahead? Well, they're independent variables. It doesn't matter if I flip one dice or I flip a coin. It doesn't matter. There's no causal effect between the two things. They're independent. So the probability of seeing both of these events is just the product of the probabilities. Okay? So if I roll one dice rolls a 6 and another dice rolls a 2, well, the chance of that occurring is specifically in that specific order is just 1 over 6 times it's 1 over 36. Or the probability that you roll a 6 and you flip ahead is 1 over 6 for flipping a 6, and probably a half for flipping a tail. And if I summed over all the different outcomes, so if all the 6 rolls of the dice multiplied by the probabilities of all the outcomes of the coin, that would all sum to 1. Okay, by this thing called the binomial theorem, if you're familiar with it, but we don't need it right now. I just want to introduce the concept of independent variables. But most of the interesting things in reality are not independent variables. So just consider a deck of cards, right? I mean, this is something that this is why you can't go to a casino and make millions of rupees immediately, because this kind of statistical reasoning is much harder than just for independent probabilities. So what is the probability of drawing a queen followed by a 4 of any suites in a card game? So so obviously if the first draw is going to be a queen, then there's 4 queens in a deck. There's 52 cards in a deck. It's 4 out of 52. But then I'm asking, what is the probability of getting a 4, the number 4 of any suite? Well, now there's one less card. So probability is 4 out of 51, not 4 out of 52. So it's not equal to the independent probabilities multiplied by each other. So the probability of a 4 and a queen is not the probability of a 4 and then probability of a queen multiplied together. It's just not true. Okay. More interestingly is 2 consecutive queens, right? So the first draw is 4 out of 52. There's 4 queens in a deck of 52 cards, but then there's only 3 queens left out of 51 cards remaining. Okay, so the conditional probability of 2 consecutive queens is very different from the product of getting a queen separate. So this is known as conditional probability. Now, something is about to happen, and it's going to happen very quickly, but do pay attention. How do we write this? Okay, so the way we write this is we talk about conditional probability. So we denote the probability of both X and Y happening as the probability. So this notation here means the probability that X happened given that Y has happened times the probability of Y, right? That should make sense, right? Is if both X and Y happen, so if both events happen, then it must mean that it's a probability that X has happened given that Y has happened times the probability that Y has happened. Okay, so this is just to distinguish it from the notion of independent variables where the probability is just factor. It's just a way of writing down what it is. But note that obviously that probability of X and Y happening is also given by the probability that Y has happened given X times the probability of X. Okay, this is just this sounds like mathematical mumbo jumbo, but look, it's the same. They have to be the same thing because intuitively, if two things happen, right, it must be that one thing happened given the other thing happened times probability the other thing happened, or vice versa. I mean, it's just word games at this point. Okay. The question that we're interested in, and this is actually bringing me to the conclusion, close to the conclusion of what I wanted to cover for today, because to begin in the next thing to do it any justice will take quite some time. So also because we've discussed so many concepts, I really want to spend some time and take your questions, and maybe I can explain things a little better. The question we're interested in, the first question we're interested in is, what is the probability that you are infected with COVID, given that you've tested positive? Now, I'm going to tell you the answer, and we're going to derive it in the next lecture. If your test has a false positive rate of 5%, okay, that means 5% of test results for truly positive people. Excuse me. So 5% of tests come back as a positive when the person was not positive. You might think that's that there's only a 95% chance that you don't have that there's a 95% chance that you have COVID. It turns out it's actually more complicated, and the probability that you actually have COVID, if you test positive with a test that only has a 5% positivity rate, it depends on what the true prevalence of COVID is out there. And if the true prevalence is, say, something like 6%, there's only a 16% chance you have COVID. It's crazy. It's actually, well, it's true. It's fact. But you have to actually see the mathematics to believe it. And so that's the first, so every time you test, this actually happens in a laboratory. When you test positive, usually that means that you're not really positive. You're probably a false positive. And then they test again, but now with an updated prior that you're no longer in a general population, you're in the category of people that had tested positive. And if after 2 or 3 times, you tend to converge pretty accurately on the outcome, on the likelihood that you are positive. So this is a very, very unusual thing to think about. And all of it follows from what you're about to see here. It sounds like something really, really counterintuitive, perhaps even magical, but all of it follows from this stupid equation here. Really, I'm just saying things in words, right? Is that the chances of 2 things happening are either something happens given the other thing times the probability of the other thing, or vice versa. Okay? Say this out aloud to yourself many, many, many times, because what we're about to do is derive one of the most fundamental theorems in statistics. And it's called Bayes' theorem. And you're looking at it right now. Okay? This is really, really one of the deepest, well, I don't even want to call, this is one of the most profound devices in statistical inference, and it gets used. It's not the power isn't in the equation. The power is in how we choose to use it and how we interpret the various quantities here. And all we've done is realize if X, both X and Y happen, then it must be that is given by the probability that Y happens given that X has happened times the probability of X, but that must be the same thing as the probability that X has happened given Y times the probability that Y has happened. So these 2 things must be equal. So let me set them equal to each other and just divide by P sub Y. This is it. This is known as Bayes' theorem. Okay. Now, it doesn't seem like much here, but as a direct consequence of this equation is what I said to you a few minutes ago, is that your likelihood of being actually positive for COVID for a test that is 95%, that only gives 5% false positives, is actually less than 16% if only 6% of the population actually has COVID. And that number goes down the more and more unlikely the population prevalence of COVID is. And not just that, if we knew very precisely the accuracy of our test and we do the true random sample, we can actually infer how many people really out there have COVID. These are all things we're going to learn by simple applications of Bayes' theorem, and you have all the mathematics you need to do it here. And it doesn't stop with just COVID. It actually goes on to allowing us to actually really learn a lot about the true nature of the uncertainty we see around us. And this is now heading towards what I alluded to, what I was trying to refer to at the beginning of the lectures, which is probability. We like to interpret it in terms of frequencies, but there's a more, if you like, I would actually say even more profound interpretation of probability, and that's in terms of hypothesis testing. And it seems like it's not so intuitive at the beginning, but once it becomes intuitive because it's so simple, your life will be changed forever. So this is all that I have formally prepared. I see we actually have something like 25 minutes left in the lectures. What I would have done actually now is, so let me just emphasize, where we're going in this next lecture, in the next week, is we're going to take Bayes' theorem. We're going to take all the formulas that we've learned up until now, and we're going to have fun. Okay, we're gonna apply it to COVID. We're going to apply it to medical testing in general. We're going to learn a lot of things, and this will be your if you like, the first pass at all of the central concepts that we've seen in data science and statistics through an example that I hope is quite close to your mind at this point. So that's where we'll begin next week. So the real fun in terms of applications begins next week. I apologize if there's two apologies I have to make. The first apology is if you already know all of this and I've been boring you, fantastic, then you're my then I don't need to worry about you. The second apology I have is if you've never seen anything like this and you haven't seen any of these notations and it seems like it's a lot and there's all these weird, funny signs that he's using to represent things, I really encourage you to go back and look over this. I'll upload the slides onto the website, look over them in your own time. I will post some exercises for you to go through, to try and understand, to try and, like Kung Fu practice, to try and, get better at Kung Fu. Just practice. You will master this stuff for yourself. I think one useful thing is, if some of you may even know each other, is to get together in study groups and talk some of the material through. On Friday, of course, or at some point to be determined, I presume it's Friday, we will have a question and answer session where we can go through all of this stuff in detail. I'll definitely have the problems and the slides up on the website before then. And also before then, if you found that my English was a little too idiomatic and maybe a little too fast, Ramiz and I will record Hindi and Marathi versions of these lectures for you to look in your own time. And yeah, so that's today. That's where we're going to pick up next week. So this is a good time to take any questions. So please just ask any questions you have.
One question is, sir, in chat box, what is machine learning?
Yeah, machine learning is a new subject. Well, it's a technique, right? So machine learning is let me think. Well, okay, let me give you an example of where it is used first, and then I'll tell you what it is. Okay, so let's say you get on some website quite often. Okay, let's say or you're browsing the internet. Then Google is dropping cookies and is seeing your web habits and seeing what you're looking at, or Facebook. Facebook does this a lot, actually. From that data, they would like to predict what it is you might like. Okay, maybe you've been searching. I don't know. You've been searching for. I don't know. You've been searching for. Sites in some particular city that's far away from where you are, and then maybe you looked up new sandals or something, then maybe it's reasonable to infer you're about to go on a holiday. And so then what Facebook and Google do is they spring into action and they try to give you more ads about where you're going. They try to manipulate you. They try to manipulate you into spending your money or visiting different sites. So that process, how is it actually done? So how it's done is that there is some computer, or if you like, a neural network is a fancy word. There is some device out there that's getting all of this data that you're giving it about your habits, and it has been trained. Okay, it has been trained on other people doing the same thing and seeing the outcomes of those people's behavior to come up with a predictive model of your behavior. And according to that predictive model, then providing you products or advertising that makes money for corporations. Okay, that thing that's doing it is called a neural network, and the process at which it's taking data and learning from it and updating some model it has for your behavior is machine learning. That's one example of machine learning. Another example is let's see. So yeah, okay. So when you so I'm not on Facebook. I can't stand the thing. So but many of you are, right? So so when you post photographs on Facebook, it'll say, oh, is it this person? Is it that person? And it gives you suggestions for who it might be. So it's tagging people for you. How does it do that? So, well, it does that because somewhere else it has hundreds of pictures of that person, and of course, there's no two pictures identically look the same. So there's a neural network, which again is just a program that continually updates its knowledge about the universe, and it's being fed with different information about a given person, and it gets trained initially. Okay, so what it is, it gets trained with so someone sends in random pictures of some random person, is training them, and the machine has to decide, is it that person? And when the answer comes yes and it's correct, they get a tick, and when it comes back yes and it's wrong, they get penalized. It gets penalized. So the machine learns from its mistakes. And that whole process is known as machine learning. And at the core is it's some sort of statistical inference for what's really out there based on some model. Okay, so a lot of data science is very adjacent to machine learning. Now, a lot of so Anup Bhai mentioned to me that there is some interest in having a course at Digital Nalanda at a basic level on this subject, and this is something that we endeavor to provide as well. But in terms of in Introduction to Information and Data Science, it's a completely separate subject, but a lot of the applications of data science are to things like machine learning. So that's what it is.
If someone wants to ask any question, please type in chat box. We will otherwise raise hand. I will unmute themselves.
Yeah. So again, I understand that it's a lot of material, and may or may not have. So either you've seen all of this before and it's easy for you, or you've never seen it before, in which case it's going to take some time to digest. That's what I strongly encourage you to do, is to go back over the slides and digest this stuff. I'm just going to quickly flash back now that we're done with the lecture. I want to just go back and show you what you've seen. You have seen all of these concepts today. These are very, very deep, profound concepts in statistics. You've seen them in a particular example. The challenge now is for you to understand the underlying principles, to internalize it, to think about it. And so the problem sets I aim to provide will hopefully help you along that process. What you've learned today, for instance, already equips you with more of a means to understand information out there than 90% of the average person. 90% of the people out there, maybe even more, right? Very simply, just applying some of the things that you've learned today. Even today, when you go on and turn on the news, maybe you'll instantly be like, "Hang on, how did they get that number? What do they mean by that number? Are they really sure they know what they're talking about?" And I hate to disappoint you, but most people out there don't. Okay, so by paying attention to this course, even supposed experts, by the way, excuse me, even people that I wouldn't say supposed experts, even people in our government, for instance, really, they need to take this course. But these are very, very, very involved concepts. And so so this is, we'll be picking up. So the reason this is now 2 lectures, not just 1, although I've alluded to many times applications to the current pandemic, it really begins in the next lecture. So we'll see concepts like the biased and unbiased estimators for fatality rates. We'll see how to actually interpret correctly the results of a test result, and how to try to actually come up with meaningful numbers to base your decisions on if you're the government. But as you can see, in just that simple application involved a guided tour of the most fundamental aspects. And as we progress through the lectures, of course, I think the majority of the basic things have been, a large number of them have been covered in this first lecture, but we will keep introducing more and more concepts as we go along. So yes. So this is just so well done. If you managed to follow me up until now, fantastic. Have a nice strong cup of chai, eat some biscuits. You've done a good job. So yeah.
Yes. Yes.
Please, Modish, please ask away. Modish Kumar, you have your hand raised. Please just ask. Unmute him. Oh, I guess you have to allow him to unmute. Is that true? Or?
Please ask your question, Modish Kumar.
Sir, thank you for describing in detail. Hello.
Yes, I can hear you.
Yes. Yes, thank you, sir. Sir, my question is, can we have something briefly? Can you explain something like what this course is all about, and what is this course going to be like, and what is the duration, and what we should expect from this course, and who is this course should join? Who should?
Yeah. So I would encourage you to go and look at the introductory session, which is online, where all of those questions will be answered. All of those questions are answered. Precisely everything you answered is there. But briefly, this I'll just mention very, very briefly. This course is aimed at anybody that knows nothing about data science, statistics, probability, information theory, nothing, and wants to understand data science, maybe even pursue it as an education or a career possibility. So it is meant to be an invitation into the subject. The first set of lectures are introductory, okay? So they assume nothing more than 10 standard mathematics. But as you can see, the concepts that we're building up are pretty advanced, okay?
Yes.
This is very advanced stuff. It's just we don't want to, confuse 2 separate subjects. So we want to give you all the basic concepts using basic mathematics. Then after these introductory lectures are over, which are primarily lectured through examples. So the examples will be covering our COVID-19, fraud detection, and election polling. Then we will prepare a more advanced stream that assumes knowledge of coding. So that we'll really, get into the meat of it. And so some students may not know coding. So we will provide a separate module or a side module to master coding. We'll have little workshops where people can help each other, and we'll run through some real life examples. And I think Ramiz and I discussed the possibility of actually having hackathons periodically in the second module, where we form groups, and every weekend we get together, or maybe every 2 weekends or something like this, and we'll work through some real life examples, and we'll try to solve them using the techniques we've learned in the course. And then finally, there'll be an extremely advanced, well, not extremely advanced, but the advanced version, where we repeat a lot of the things that we did, but with the knowledge of calculus. So So we'll have to teach calculus as well at some basic level and what is known as linear algebra to set students up for if they want to then go on to do more advanced things like machine learning and artificial intelligence, which is ultimately our goal for this school. But the way to think about it is anybody who starts from zero can begin at the beginning and go get everywhere. Our goal is to not leave anything unexplained. So please just go and look at the introductory lecture, and all of your questions are addressed there in some form.
Okay, sir. Thank you, sir. Thank you very
problem.
much.
Are there any
If
other
anyone-
questions? Yeah. Go
No
ahead.
question.
Okay, well, if there are no more questions, then please, please feel free to just, when we have our question and answer sessions, come and talk to us, or even if you just want to log in and say hi, just have a conversation. Very happy to chat. Ramiz and I are both very friendly guys. So it can even just be, virtual coffee if you like. But also, please do, if you find that this is stuff that you're, please go over the lecture slides before every subsequent lecture next, because this will start basic, but will get very fast, very quick. Okay, so because we're trying to cover a lot in a small number of lectures, and I also, emphasize that, just to say it one more time, although we have only assumed that, we're not going to assume more than 10 standard mathematics. These are some extremely advanced concepts in mathematics that you're seeing. And so, you should feel very proud of yourselves if you've understood it. If you haven't understood it, that's okay. Nobody understands anything the first time they see them. I certainly don't. So spend time understanding it. And if you're finding that there's something that either me and Ramiz didn't explain well, tell us. We're happy to spend as much time as possible as it needs for you to understand what's here. Okay, because our goal is to really, is to build up. Is to build up your knowledge of this very exciting subject with very many possibilities for professional and personal advancement. And I would just like to stress, even if you're not considering a career in data science and you're just taking this class for fun or for knowledge, the knowledge you'll learn here is going to be priceless. I mean, I learned a lot myself from this, and I navigate the world now with a lot more confidence than I did before, because I don't believe half the numbers I see when I read about them in the news. I'm just like, come on, no. Let me find out more about them. And then I go and I think about it, and I'm empowered to come up with my own conclusions, and that's something that we want for you. So if that's it, then that concludes today's session. Dheeraj, do you know if we're having a session on Friday for a question and answer?
Yes, sir. But one question in chat box.
Oh, okay. Please go ahead.
Can you suggest some books or website to brush up the concept?
Yeah. Okay. Well, I mean, I think the problem with that is I'm worried about giving you things that are a bit too advanced. Well, I don't want to distract you with too much information, at least at the level of these introductory lectures. Let me think about that. I'll try and find some resources. I think ultimately, one should view the presentations that we're giving here as self-contained lectures. So a combination of the slides plus the problem sets should be self-contained enough. There's a lot of words I'm saying that are not recorded on these slides. Okay, well, they're recorded on the lecture, but they're not recorded on the slide. So one way for you to learn yourself is to pretend like you're in a real classroom and take notes. For more advanced reading, a lot of the concepts I covered, for instance, it really depends on how comfortable you are with mathematical notation. Wikipedia is a fantastic place to start. But let me think about that. So and by the way, if any students have a suggestion for a good textbook, please let me know. But to my experience now, I haven't found one that makes me completely happy. That's why I haven't suggested one. And ultimately, maybe if you see, the problem is I have many responsibilities with my actual job, including teaching, and so I just physically don't have the time to prepare lecture notes as well. But I'm hoping that if you pay enough attention to these lectures and do the problem sets, it should be enough. So the problem sets I will set will have some explanations there as well. So it's not going to be, somewhere between a lecture notes and a problem set. But so to answer your question, I need to think about it. But do try and understand as much as you can from the lectures themselves.
Yes, sir.
Yeah, so I guess that's it for today. So thank you very much for attending. And Friday we have a question and answer session. Even if you have no questions, just please log in and let's just chat. I'd love to meet you guys and talk to you more personally. Okay. So have a good week, everybody, and see you Friday.
Okay.
Hello, now. Bye, everyone.